I am starting the recording. Okay, so welcome to week 4, everyone. How's everyone doing? We're all good. We'll be looking at power transmission this week. So power transmission is basically moving power from where it is, the motor, to where it needs to be, a wheel or weapon or whatever you're trying to move. Like, we can change the torque or the speed at the same time, and we're going to look at 3 different methods: gears, belts, and chains. So first of all, this is what a motor looks like. You put in electricity and this thing spins. It's about as simple as that. Well, it's got a lot of complex things on the inside, but we won't be taking a look at that. You can attach things to this thing over here to make those other things spin. Pretty simple. Okay. So, well, in more technical terms, it converts electrical power into mechanical or rotational power. How do you choose a motor? A motor has a lot of different specs that you want to take care of. So kV, I don't know what exactly it means. I've heard 2 different things. It's either the constant of voltage or the constant of velocity. But what it basically means is how many RPMs a motor makes when 1 volt is applied. So RPM per volt determines how fast your motor will spin. Higher kV equals to lower torque. So if you want more torque, you got to pick a lower kV for your motor. Power implies how fast work is being done. So power is current times voltage. Higher power generally gives you a faster spin-up time. So like when you're just starting your robot, you want it to reach its max potential faster. So you pick a higher power for your motor. Yeah. Max current, the highest current. Oh, where's my screen? Max current, the highest current that the motor will draw continuously. Max voltage, stall current is the highest current the motor will draw at 0 RPM. It's like stall current, kinda. Like if your motor is not moving and your current is stall current, you could end up damaging the motor. Like the motor could not be moving because of physical constraints. Max voltage is the highest voltage battery that you can use with the motor. Power depends on the voltage, but you don't have to use the max voltage every time. But there are some kinds of motors where you have to use the max voltage and then you PWM the signal from the battery instead. So there is a useful website in that link. We'll look at that later. So this is what a spec sheet looks like. Any questions? You don't need to know all of these numbers, but like we've pointed out, the stuff you might want to look at when you're choosing a motor. So I hope everyone's clear. Any questions? Okay, I hope Kyle and Keaton are handling it in chat. Okay, so how do you interpret these numbers? To get more power, you need more current or voltage. Does anyone remember the formula for power we saw 3 slides ago? I hope people are answering in chat.
We've got one answer for P equals IV.
Okay, yeah, that's good. That's right.
Hell yeah.
Okay. If you have a heavy load, though, you might want less voltage for the torque. because if you keep applying a higher torque for a really heavy load, you could end up damaging your motor. And always just ask the electrical team. Like, I'm living with 3 electrical roommates, and they talk a lot about stuff that I don't understand. But like, when it comes to motors and stuff, they also don't understand some of the stuff that I know. So it's good to communicate with them. Okay. Power transmission. So gears. Gears. I understand gears instinctively, but putting them in words is a bit difficult for me. Gears are used to transmit power across parallel or perpendicular shafts. So the shaft goes in the center of the gear, and you can have your shafts parallel to each other. And depending on the thickness or, well, not thickness, well, the gears have to be in the same plane as each other if they're parallel. And if they're perpendicular, they just kind of have to meet at the like pitch diameter. It's useful for situations with high torque, such as if you're using a belt. Sorry, not a belt, a chain. Belts can slip. A chain can go on a gear. Anyway, torque and speed are inverses of each other, so you can increase the RPM at the cost of lower torque. Or you can connect 2 gears side by side to each other, such as over here. In order for 2 gears to connect, they should have the same tooth profiles, as in the teeth must mesh. And so then you'll usually have 1 gear that's driving and 1 gear that's being driven. So in this case, the first gear is driving, like that's where the motor is connected, and the second gear is where your output is, like maybe that's where the weapon is or whatever you're trying to move. And so gear ratio is a ratio of the number of teeth of the number of teeth of the second, the driven gear, to the number of teeth of the driving gear. You can also compare the diameters, but the teeth are generally designed in such a way such that slight differences in diameter don't make much of a problem. Like, for example, if you compare the diameter of these two, maybe you might get like 1.95 or something because they're not accurate. But if you compare the number of teeth, you'll just get a nice clean integer 2. And so that's the more important number. So you compare the number of teeth for more clarity. And also it's just kind of easy to remember. Larger gears move slower, smaller gears move faster. So even if you forget this formula, you should just kind of keep that much in mind. And so this is what we meant earlier. So these gears are parallel to each other. These are spur gears. Their teeth point outwards, radially outwards. And they usually have low gear ratios, but they're simple and very efficient. Bevel gears are perpendicular to each other. And as you can see, their teeth are also somewhat at like a 45-degree angle. So these also have high efficiency, but like you have to make sure your axles are aligned properly. Like these axles also kind of have to be in the same plane. And a worm gear and a worm. So this is also perpendicular to each other. So you cannot drive the worm with the worm gear, but you can do it the other way around. So this also has kind of a high gear ratio, because the worm has effectively 1 tooth. It also has a lower efficiency. I think you can imagine the kind of problems that arise from trying to align this. Any questions so far? Okay. Like just Kyle and Keaton, like if there are any questions, feel free to stop me as well. Okay, moving on. So this is a planetary gearbox, a system of gears. There is a central sun gear. There are these planetary gears, and the shafts of the planetary gears are all attached to this central carrier. then there's an internal gear, which is sort of like the outside solar system. And so like you can stack like just 3 or 4 gears together to create really large gear ratios. And in this case, as you can see, the carrier is moving depending on your combination of parts and stuff. You can have any one of the 3 parts moving. So like the sun gear just spins in place, and this internal gear is just stable while these things moving. You could probably just change a couple of things, make these 3 gears stay in place and the internal gear rotate instead, etc., etc. And then spur gears in series. So this is also another way of sort of increasing the gear ratio dramatically. So as you can see, here's a large gear, here's a smaller gear, but the smaller gear is also just connected to this large gear. So what this means is this small gear and this large gear will have the same velocity. They'll have the same angular velocity. And so as we know, like large gear moves slower, smaller gear moves faster. So if this is what you're driving, then this will move faster, but this is, and so for the third gear, you'll consider this to be the driving gear, and this will become the driven gear. So this is smaller, so this will move way faster. And like you can just keep connecting as many gears as you want in this line. Oh, here's a cool example. This video is like 10 minutes long, so we're not going to watch the entire thing, but here's a good example. So this one has 24 teeth, this one has 8 teeth. Okay. This one has 40 teeth. And so this is how you multiply the gear ratios. So since this one was just like the previous example where you had a small gear and a large gear connected together. So if you're comparing the ratio of the second and third gears, you take 40:8 because you're using the small gear here. And so these are all gears. Yeah, these are all gears with 40 teeth, but using the smart combination of gears, you're getting a gear ratio of 375. Okay, let's skip forward just a bit. Okay, this is a worm gear. Now we're obtaining a gear ratio of 720. I believe this is a planetary gear. Oh, no, okay, it's not a planetary gear, but it shows you like an internal gear. So here we have a worm gear that's connecting on the inside. You can apply the power of the worm gear and it's a ratio of 168. Cool. Yeah, and there's like the slight gap, but the teeth can still match anyway, so it doesn't make much of a difference. This scans. That's not right. And yeah, they're applying force in the small gear at the very center. And it's the final ratio that we're getting. Ratio of 1,685 at massive. Anyway, let me just show you the final. And there's the big picture. And so they've made a Google to 1 gear ratio. You can check this video out later. It should be in the presentation itself. But let's move on. So any questions about gears? Okay, I have pretty good. Okay, moving on. Belts. Belts are generally used with pulleys like these, and you can use them to transmit power to another shaft, similar to gears, but they only work along parallel shafts. Now you can't attach belts perpendicularly. So again, similar to gears, you can change the torque and speed as you want. The same ratio rules apply, and we have 3 different kinds of belts: a flat belt, V-belt, and a timing belt. So a flat belt, well, it's basically flat. You generally have these flat wheels to go along with the flat belts, and the pulleys need to be aligned on the same plane. Like with the gear, the teeth of the gear, they can be slightly offset, but pulleys need to be really aligned, otherwise the belt will just slip off. Well, slide off. So the belt generally has a thin cross-section and high efficiency, and you can just run it on an entirely flat surface. And you can make the belt fit into a shallow inset in the metal, and it can help with the belt creep. So the belt creep is where it just slightly moves around. A V-belt has this sort of V-shaped profile here, like there is a groove in the wheels that you stick the belt into, because that's like easier to keep a belt in a groove than on a flat surface. But because of the V shape, like there is more friction along these walls, and so that means it's not as efficient at higher speeds because of the high friction. So it's slightly less efficient than a flat belt. And you need to maintain lower tension because of the same reason. So we already made a V-belt from the week 2 CAD guide. I hope you guys remember this. Okay, a timing or synchronous belt. This is best used for lower speeds when you want absolutely no slip at all, but you can do with lower speed. It's useful for meshing with gears or pulleys, which have teeth that correspond to the kind of belt profile. And there are like 3 kinds of teeth on the belt. So even these belts have this sort of pitch, which is the difference, the distance between the teeth. There's trapezoidal teeth, curvilinear teeth, and modified curvilinear. So they provide the same kind of engagement as chains can do with gears, or gears with each other. It's useful when positioning, indexing, or a constant speed ratio is necessary. So chains are also similar to belts, but they have these teeth along them. So they also transmit power only along parallel shafts. You can't connect them to perpendicular gears. And they can also change their torque speed based on the same rules as a gear ratio. Ooh, of course, there is a slight difference for belts and gears, the direction of rotation will stay the same. So if this gear moves counterclockwise, this gear will also move counterclockwise. Whereas if you just connected the two gears together, one would be counterclockwise and the other would be clockwise. So it depends on how you want your parts to move. Oh, another thing I wanted to mention was, let's say your gears have to be this far apart from each other. There are multiple different ways to connect those gears to each other. For example, the chain is an obvious one, but you could also just add a third gear in between these two, right? So with the chain, these two have the same direction. With a third gear, you could have this moving in one direction, this moving in the opposite direction, and this one moving in the same direction. So you could effectively achieve the same goal. And with varying numbers of gears, you can also just change the direction of rotation. So let's say if you had 4 gears, like 2 at the end and 2 in between, then the final gear would have a different direction of spinning from the first gear. So that's something chains cannot do. But a chain would be much lighter than having all those gears in there. So that's a trade-off that you should consider. So we compare belts with chains. What are the advantages that belts have? Belts are, of course, smoother and more flexible, and they slip on impact rather than putting stress on the motor. This is sort of important for battle bots in particular. A chain does not stretch over time, and since chains are made out of metal, they are generally not affected by high heat, and they also have greater tensile strength. The disadvantages of belts and chains are kind of the opposite. Like, one is good at these other things but bad at something, and like belts are good at some things that chains are bad at, and vice versa. So belts are easier to snap or cut through, and they require adjustment time and time again, because as you keep using it over time, your belt will stretch. A chain weighs more, and it doesn't slip on impact, and transmits torque directly to the motor on impact. So as I mentioned, for battle bots, if your weapon is being driven by a chain, and your weapon makes contact with the opposing robot, like, you don't want your chain to just transmit all of that torque directly into your motor, right? Because as soon as you make contact, your weapon is going to stop moving. Like, the velocity will become 0. And that is a sharp deceleration that your motor probably cannot deal with. And so in such a situation, you want your power transmission to slip from the motor, because that protects the motor. Okay. Oh, any questions on belts and chains? Okay. I accidentally refreshed this. That was not meant to happen. Okay. Okay, sorry about that. So, moving on. Constraining shafts. So all these things we've seen, gears, belts, chains, and pulleys, they all need to go on an axle. So how do you keep things on that axle? You generally need to constrain these components in 3 directions. So axially means along the axis of your shaft. Oops. Oh, can everyone see that pointer?
Yep, we can see it.
Yes.
Okay, cool. Yeah. Radially means going outwards from the center, and tangentially means you don't want it to slip with respect to the axle. So shafts are generally retained radially by bearings or bushings, so we don't have to worry about it. This is a ball bearing. Bushing is kind of similar. And often one accomplishes the other. Like if you constrain it in one way, you also tend to constrain it in another way because of like how much friction there is. So these are different methods for retaining shafts. As you can see from last time, this is what a set screw looks like. We look at it further. So this is an interlocking D shaft. As you can see, the profile of the shaft has this D shape over here. And so this thing also just has a corresponding D-shaped hole. So the retention depends on the exact method, but generally you're constraining this tangentially, as in this does not rotate with respect to the shaft, and axially, like it cannot move along the shaft after you've tightened it. The strength, it relies on the strength of the material, so it's generally some of the strongest methods for retention. However, it does add complexity to the manufacturing, because generally creating these D-shaped holes is a lot harder than just creating a circular hole. Okay, set screws. Yay, we looked at set screws last time. It requires a flat side on a shaft, so you could use this with D shafts as well, because they also have a flat side. Well, they have like a flat surface. And it retains components axially and tangentially. So same as before, it does not rotate with respect to the shaft, and it does not move along the shaft. But it's usually based on friction. Like you see this part pointing out, that thing is what like it just rubs against the shaft, like it uses friction to hold it in place. So it's usually better for low loads. A retaining ring or a snap ring, it requires a groove in the shaft. So there is a groove. Oh, this part, if you can see it. So that's where you can stick the snap ring in, and you can sort of tighten it using pliers. And it restrains components axially, like it prevents things from moving along the axis. A shaft collar. So this can be used on any kinds of shaft. You don't need to modify the shaft, like it doesn't need to have a flat surface or anything. You just tighten this screw over here, or you like buckle this part over here, and that's how you get things to prevent, like you can prevent things from moving axially as it gets tighter. And finally, keys. Keys retain components tangentially. So like as you can see here, there is a square-shaped hole here. There is a square-shaped hole over here as well. And this key is supposed to like fit between both of these. So you can imagine that without the key, you could put this in and it would just rotate as is. But when these holes are aligned, you can add the key in there and it'll just stop it from moving tangentially. It'll stop it from rotating with respect to each other. The problem is that keys increase manufacturing complexity because like there's more parts to worry about. And let's see, you can search for shaft key chart to see corresponding sizes. So yeah, there are different kinds of key slots. I hope you all guys know how to match shapes according to their holes. If not, please complete kindergarten first. The square holes, like the sort of curved concave hole, etc., etc. Okay, and this is the weapon from Valkyrie. It's a horizontal spinner. So we have different weight, like attachments here. This is a shaft. and there's a set screw that connects the central part, and there's a hole for this set screw as well. So like along this central part, like there's just this one hole where you can insert a set screw, and there is a small part cut out here so that you can press the set screw against this. There is a D shaft cut down at the end as well, so that thing can be pressed into a corresponding D hole. And speaking of stress, puzzle fits. It uses interlocking perpendicular pieces to secure assembly, like these sort of square rectangular things you see here. Those are just fit together, and they're sort of like pressed together, and it relies on the strength of the material again, so that's why we use it in BattleBots often. Like, screws are not as reliable because all the stress is concentrated in the screws. So this one allows you to sort of have a wider surface area, and so that reduces the stress. And so, any questions, comments? I hope we're all good. Okay, well, it's time for the Kahoot then. I will temporarily stop presenting my screen.
It's go time. Let's do it.
Okay. And player versus player. Okay, and we have a pin. Okay, can everyone see the pin? Okay, sweet. Yeah. And people. Okay, I hope that's all. So let's get started. If the shaft is spinning, but the gear is not, what constraint is lacking? So imagine the shaft is spinning, but the gear just stays in place. What's your problem here? Yep, that's right. It's not tangentially constrained. So this is the tangent of the shaft, and the shaft is moving, it's rotating, but the gear is not moving with it. So that's not tangentially constrained. On to the next question. Ooh. If the gear on the left is the driving gear, i.e. on the motor shaft, is this geared for speed or is it geared for torque? I hope you remember what I said about the size of gears. That's right, it's geared for torque. So smaller gear moves faster, bigger gear moves slower. And so if it moves slower, it's got low speed, it's got higher torque then. Okay, so yeah, as you can see, a smaller gear can produce a higher torque when you combine it with a larger gear. That's good. The gear on the left has 7 teeth, and the gear on the right has 21. What's the gear ratio? Left is driving. This is where your motor is. Yep, that's good. We've got 21 over 7. Think of it this way. It's output over input. This is the output. This is the input. Output over input. You get 3 over 1. That's good. What kind of power transmission is theoretically best to run this BattleBot's weapon, which is run at very high speed? Didn't we just see this weapon? Pay close attention to this wheel. Yep, that's right. It's a flat belt. Just correct me if I'm wrong, Keaton, but there is a flat belt that goes between these two discs, like it aligns along this wheel over here, and the flat belt can spin at very high speeds, so it spins this weapon along with it. Okay, cool. Next question. True or false? One disadvantage of belts is that they transmit any torque applied directly to the motor. It is, in fact, false. Like, any torque applied directly to the motor, which means if your weapon just comes to an abrupt stop because it made contact with the opponent, your belt will slip, thereby protecting your motor. That's good. Next question. Ooh. What does it mean for a motor to have a relatively high kV? What do you get if you have a high constant of voltage or constant of velocity? Can achieve a higher RPM. It usually means it can achieve a lower torque, not more torque, but higher RPM. That's good. Okay, which type of gear system allows for crazy high or low gear ratios to be easily achieved? I think easily here means how many gears you have. That's right, a planetary gearbox. So you need one central gear, one outside internal gear, and however many planets as you like. Generally 3 planets. That sort of minimizes the number of gears you might need. Now, if you have like really large spur gears, you could also use spur gears in the series, but generally planetary gearbox is more efficient. Which is not a property of a chain? Does it should have time? Is it directly motor? It's not. It's just suddenly stop. Which is not a property of a chain. Yep, that's right. The chain generally meshes well with the teeth of the gear, so it does not slip. And let's see, that's good. Stall current is the highest current the motor will draw at maximum. True or false? is false. Stall current is the highest current the motor will draw at 0 RPM. Remember, if your motor's not moving and you put too much current into it, you will damage your motor. So stall current is sort of like the upper limit of that current that it can take when it's not moving. Okay, which two shaft retainers prevent tangential movement? Remember, tangential movement means the axle and the wheel would move independently. You don't want that. Ooh, that is correct. D shaft and key. Looks like there's a mix of answers on this one. So yeah, D shaft. This is a D shaft. Because of this flat part over here, it prevents this wheel from moving with respect to the shaft. And a key, similarly, this key will prevent this inner shaft from moving with respect to this ring. A set screw should also work. This one will not prevent tangential movement, though. So yeah, we've got first place for Natalie, second place for Marvin, third place for Brian. Congrats, guys.
Oh yeah, good work.
Mm-hmm. Ooh, there was. Oh. Okay, any questions? Just let me quickly check chat. Ooh, we called set screw shaft collars. Okay, let me just quickly pull up the image. Not here. Ah, sorry about that. So this screw is the set screw, and this collar here is the shaft collar. I hope that clarifies it a bit more. All right, cool. Okay, so week 4 CAD guide. Let me start presenting. So this week we're gonna make a steering wheel. So we might use a few lessons from week 2. And this is the sort of wheel we want to make. It's got these 3 spokes, it's got the central part, and the wheel itself. And it's got this sort of knob over here. This is what it looks like from the top and from the side. Okay. So first we will create this sketch here. It's sort of rectangular, but it has this bump in between. You'll see where this bump comes into play. Like, there are a couple of different ways to do this, but this one requires the least amount of features. So for this sketch, you will rotate it. Rotate the sketch along this right edge. Oh, along this right edge. So now, to set up your sweep, you will just create this sketch over here. It's just a standalone sketch. Like, that's the first part of your sweep. And then you want to create 2 planes that are perpendicular to this sweep. So there will be one plane over here and one plane over here. These are those 2 planes. And then you want to draw like the profile of the spoke. So that's so you'll just make a sketch on one of these planes. And then you sweep using that path and sketch. And so this is how you get. And you can use a circular pattern to make the 2 other spokes. So you create one, and then you just use a pattern to duplicate these. Ooh, and remember to add a work axis in the middle, because that'll be useful for a lot of things. So making the wheel itself. So sketch a circle where its point is around here. The center point is around here.
And you don't really need any dimension constraints, just whatever you like. And revolve it around the same work axis. So this is your axis we made previously, and you just revolve this around the work axis to get this wheel. Okay, so now finishing touches, just chamfers and fillets. Make everything look a bit fancy.
So the sort of flat edge is a chamfer. The fillets are the more curved parts. And over here as well. And like, let me just go back. Yeah, you can sort of select a distance for your chamfers and fillets. Where's the fillet? 10% fillets. Oh yeah, more chamfers over here. And now creating a wheel spinner or a Brody knob. So that's the knob we saw earlier. So just create a new work plane that is like on top of the wheel, just like on the top surface. And sketch a base of a spinner on a new plane, like something over here. Just this small square thing over here. And just pay attention to the extrusion details. So like it's extruding in both directions, and its total thickness will be 3 inches. And then more fillets and work plane. Oh, you're making a work plane on top of the extrusion. Details for plane not provided. Use only elements from the base of the spinner you just made. So yeah, just use the surface for making your spinner. You don't need dimensions. Revolve spinner handle. So yeah, this is what the spinner's sort of cross-section looks like. You create this sketch on top of that new work plane that you made, and then you revolve it along this axis. And this is what you get. And you just apply a fillet, so it's just not just a flat disc. And voila. You can also just add some properties, like make this material aluminum. And if you like just set aluminum 6061, you'll get most of these details automatically. And that's it. Okay. Any questions? I will stop sharing my screen then. Okay, so yeah, that's it for today. We do have some 10 minutes left, so feel free to hang out or just whatever.
Thank you, Sean.
Cool.
Maybe.
Cool. Bye, guys.
Bye, Ray. Thank you for coming. And then there were 4.
All right.
Okay, just us left. Cool.
Yeah, I got an exam to study for, so I'm gonna go hit it up. Good job, Sean.
Yeah, cool. Thanks. See you guys.
See you, everybody.